I'm presenting today on the advances in the measuring pyrethroid residues and bioavailability through the use of stable labeled internal standards. Presenting on behalf of the Pyrethroid Working Group. There's an increasing interest right now in the quantification of pyrethroids due to questions about their potential impact in the aquatic ecosystems. In order to address some of this, there were recent advances in research have been made on behalf of PWG in developing methods to utilize the stable internal standards for the determination of residues. We're utilizing 9 major AIs. Matrices to be covered today include sediment, water, and wastewater systems, biosolids, solids, effluent, and influent. In addition, we utilize the stable isotope standards to allow for SPME-based quantification of both total and bioavailable residues. Pyrethroid Working Group is a task of members that includes 6 registrants. The active ingredients we were looking for are bifenthrin, cyclothrins, amongst all these that are listed. Currently, there's a wide range of classical methods that are available for quantifying all of these different methods. The methods utilize extraction, which can vary by a matrix. The extraction steps may be followed by various degrees of co-extractives, and most frequently we're utilizing NCI or negative chemical ionization GCMS detection. This type of detection can be challenging. The extent of the ionization intensity or enhancement and suppression can be impacted tremendously by the presence of co-extractives. This leads to sample-to-sample variation, requires conditioning of the GC system in order to create acceptable chromatography and minimize the variations throughout the run. It requires more frequent instrument cleaning because we can't maintain consistent standard response, so over time it's critical to work on the instruments, keep them going, so time and money is critical at this point. Consequently, the PWG has investigated the use of these D6 internal standards for all of the 9 AIs mentioned. So in order to appropriately select the targeted AIs, we took a couple of factors into consideration. Number 1, we needed to locate the location on the molecule to be the primary target ion of each compound for analysis. So we had it in the detector, the leaving group. We wanted to make sure we had the stable isotope moiety. The difference in the molecular weight also needed to be such that the target ion was at a mass value for which the native had none to minimal response. We had the D6 analog synthesized to meet these requirements. The primary target ion was met, so we did have it in the correct position. And the molecular weight differential we came upon was a +6. It's a deuterated +6. So that was important because some of the pyrethroids, such as cypermethrin, contained 2 chlorine atoms, which in turn give you a +2 and a +4 response in the detection system. So while we're monitoring for that, we're at +6, which in all of the aforementioned AIs, there was no response. We also had confirmatory ions, so with this we've gained a lot of advantage. Here is an example of some of the compounds that we deuterated. I won't go into great detail for the sake of time, but you can see where the compounds cypermethrin, S-phenvalerate, and phenpropythin were added the deuterated compound. We incorporated these deuterated analogs into all the methods described in this webinar as an internal standard. We mixed the D6 standards to be used for, we reconstituted all of the samples with this mixture in the final step, with the exception of SPME. The response ratios of the pyrethroid, the native pyrethroid, to the corresponding D6 internal standard are then compared to the ratios of the standard that have the known native concentration and the same IS concentration as the sample extracts. Because of the near identical chemical behavior of these D6 compounds, It gave us a very accurate ability to correct for fluctuations or drift, as I noted earlier. So into the matrices at hand, we did a runoff study in 2011, 2012. This analysis was challenging as we had large water samples that we extracted into hexane. We had about a 500 times concentration factor. There was a variability in the runoff water, as these were waters that ran off simulated house fronts into a gutter and were collected in an underground sampling system. So the variability in the sample wasn't pure water. And it was an extremely high production study which generated near 3,000 samples over the course of the study. We targeted LOQs for this method in the 2 to 20 nanogram per mil or ppb range, and incorporated all of the AIs for the study, with the exception of the validation, at which time we did not have lambda-cyhalothrin, which was being synthesized. So what I'd like to show you here is a couple of the net results for deltamethrin, lambda, and permethrin. As I noted earlier, the D6 was not available for validation. The recovery for the deltamethrin was 91 on average. The permethrin was 94 on average. However, the lambda-cyhalothrin was higher at 114. For the actual runoff study itself, all of the compounds did have the internal standard, and we were able to maintain a very steady overall mean for all recoveries with a very tight standard deviation. So what that meant is that it was highly successful in using this internal standard. The lambda-cyhalothrin recovery improved from a high mean recovery at validation of about 114% to the mean recovery of 90% for the runoff study when we actually had the D6IS. The recoveries for the deltamethrin, which incorporated it, and the permethrin prior and during method validation show very similar results at validation and over the whole term of the study. So the overall range for the AIs in this runoff study were 87 to 94%. They were very tight in the RSDs, and the variability in the responses created by this instrument over time were stabilized by the use of the D6. So it was a very successful study. So these D6 isotopes were critical in maintaining the high production, as we did over 3,000 samples. It was basically a daily analysis for 2 years. Minimal injections were required because of variation. Another study that we performed for the PWG was a round robin of 32 publicly owned treatment works, or POTWs, by Morse Laboratories and CalTest. The matrices we were dealing with were biosolids, effluent and influent wastewater. CalTest used a different method than ours, but we both had the internal standards. This was problematic in the sense because the samples were completely different from each POTW, and the handling processes in each of those sites was different. So when the samples came in, they were notably variable in composition from sample to sample. It was very difficult on the samples themselves. But a particularly difficult issue is that these samples came from actual real and live sites, and they typically contain trace residues of many of these pyrethroids that we stated. Because of this issue, we derived a scheme in which we used some of this D6 labeled material to use as a surrogate. Here I've defined by the EPA definition what a surrogate is. I won't go into great detail because I believe most of you would understand what it is. But what we did is we utilized the S-phenvalerate and the phenpropanone as surrogates. We utilized these because minimal use of these compounds was used in California, so there was a less likely chance that it would appear in the samples. So what happened is that it precluded them from being used as an internal standard throughout the study. So we worked on it, and we experimentally determined that the bifenthrin and deltamethrin analogs were acceptable substitutes for these compounds we use as surrogates to be used as internal standards. Here's what we use to analyze the biosolids. They're very difficult because the biosolids are typically treated by the POTWs with a flocculating agent, so they were real tightly bound and extremely difficult dirty matrices. We utilized methanol to extract. We did multiple extractions with methanol and dichloromethane, a couple of cleanups, but the essential key is that we reconstituted all of these with the cyclohexane D6IS solutions. Here are the results of the concurrent fortifications. We had a LOQ of roughly 20 ppb, but we fortified in the 200 ppb range. For the concurrent studies, what you can see here, we had six with varying LOQs. The surrogates are shown here. We could go to a lower LOQ because there was limited background of 25 ppb. However, the average recovery is tight. It was typically 80 to 85% with a very similar standard deviation. The surrogates that we utilized throughout the entire run, which had 27 replicates, clearly showed the method was in control, but also certified that we were getting good data. So basically, this here covers what I just stated, so I'll just gloss over it again. But ultimately, what it did was show that we had two uses now for the D6 surrogate standards. The effluent was also run. You can see that the averages of the recoveries here were very good. Also, the effluent was still dirty as it was the sewage system coming into the POTW, so there was a high variability in that content also. We had varying degrees. We could go lower in the LOQs. This was a hexane extraction of a water methanol base. The surrogates were very good in line as procedural fortifications, but also in utilization as a surrogate for all the different trials. We maintained a recovery of 87 and 89, which is consistent with the procedural fortifications. The influent, this was the cleanest of the bunch. However, it still showed similar trends. Surrogates were optimal and worked as we would have expected. So in the end, the surrogate recovery results overall supported our conclusion that the methods were well under control, and we were able to generate valid results from samples of variable compositions, which were extremely dirty. Also, the average recoveries for all of these AIs in these difficult matrices fell well within recovery range that are considered acceptable by EPA of 70 to 120, while rarely did we deviate outside of the tight norm we saw. So in the end, the use of the D6 standard, it stabilized the instrument variability in very difficult matrices. Both labs utilized it. They were critical to this successful study, and in particular, we found a new use for the D6 as a surrogate. On to sediment studies. Multiple studies have been reported over the years in support of PWG studies regarding sediment. They supported a lot of Lenwood Hall's work provided by the PWG to analyze these sediments in pyrethroids. This original method did not incorporate the use of D6IS. It was very difficult to run. Instrument variations were due to extreme differences in the sediment, which could have been sandy or clay, numerous situations. This was a precursor to all the work that was mentioned above. So we modified this one eventually to incorporate the use of the D6IS and eliminated all the issues we saw previously. And typical recoveries for this range in the 80 to 90%. On to SPEME. There's been a really increasing recognition of the importance of measuring freely available concentrations of pyrethroids in water or pore water. Potential for these pyrethroid residues in sediment to impact invertebrates in the ecosystems depends a lot on the freely available concentration in pore water. The most convenient method to achieve this is via solid phase microextraction, as demonstrated in Jay Gann's laboratory, and will be further expanded in the following presentation. Following slides will show how using the D6 labeled material allows estimates of both the free and the total pyrethroid concentrations in a single step. Here's an example of the work we've been performing recently. We fortify sediment samples with the native IIs on the sediment, add the supernatant, perform an overnight, basically, well, the supernatant is added the second day, but regardless, what I'm trying to show here is that the pore water is separated, and to that pore water we add the D6 internal standard. From this pore water we can determine C total and C free. The instrument utilized, again, is a negative chemical ionization GCMS. We used a Gersel autosampler, which incorporates the SPME with a fiber that will come out and place itself down into the autosampler vials. The automated system will then shake it and do numerous and hold it in the vial for a time, and it will absorb the matrix, as I'll show in the next slide. The slide simulates the autosampler vial that I showed in the previous. Here's an example of a pyrethroid and the deuterated pyrethroid. We get interaction between these two compounds on the container walls of the SPME, which if you work with pyrethroids, you know that they're going to come out of the water system and adhere to the walls. Suspended solids will also bind to these compounds, as well as some of the dissolved organics. The SPME, the premise here is that there will come an equilibrium with the native and the deuterated, so that we can then calculate the ratios to determine our final results. These also interact with the SPME fiber itself. Here we can show how we determine free. The free is basically a comparison of the free of the native with known concentrations, and we extrapolate the data from that to determine the free in the deuterated compound. For the total, we use the ratio of the native to the D6 to concentration in the sample versus the actual standard. This all occurs concurrently. So what SPME allows us to do is it allows us a very rapid measurement of the free pyrethroid, which is what is bioavailable and critical for understanding the aquatic risk. And because it's essentially identical, the D6 to the native, it has been shown through experimentation to exchange extremely quickly for both free and that absorbed. We can use it as an estimate of total by classical isotope dilution techniques. Therefore, by adding the D6 material to the same sample in the SPME assay, you can simultaneously generate values which we have shown to be statistically indistinguishable from large-scale LLE extractions to that of a simple SPME analysis. One 18 ml solution of SPME allows us quantitation of both free and total, whereas to extract we need to generate 180 mils at a minimum and run 2 sets of operations simply to obtain substrates like the pore water. In the toxicity tests. So ultimately, in conclusion, we have current PWG methods which are based on the negative chemical ionization chromatography GCMS with use of the D6IS to normalize instrumental response. The following matrices were covered in this presentation: sediment, water, and the wastewater systems. We use the D6 standards to exploit the development of surrogate methodology, which allows us to give an assessment of method performance as well as to get good overall recoveries to support the use of the surrogate. By using these, high-quality estimates of free and total pyrethroid concentrations can be determined simultaneously through the use of speeming with a minimal sample volume. And essentially, the success of all the aforementioned projects was by the use of these D6 analogs in the analytical methods. Please contact Delcoke if we are offering free trial quantities of the 9 D6 materials if you're interested, and also for a copy of this presentation and copies of the analytical methods that were described in this webinar. I'd like to acknowledge the Pyrethroid Working Group, and particularly my co-authors Paul Hindley, Tianbo Zhu, and Delcoke. Thank you very much.
Thank you very much, Kevin. That's wonderful. I had one. I don't see any questions in the queue at present. If the audience would like to type in questions, that would be great. And in the meantime, I had a quick question about the addition of peanut oil into the extraction method. Can you explain why you use that?
Yes, what that was used as it was a co-additive to help on the injection of the compounds themselves. What it helps is to condition the injector port. So realistically, it was used in the beginning with the sediment methods without the use of the internal standards to help normalize or mimic some of the matrices and the standards themselves. So as we've progressed, it doesn't hurt anything, so we've left it in there while we still use D6.
I see. There is a question that's come in, a couple of questions. It says, is there any data on internal standard area drift during analysis? So I'm assuming that would be sort of during a sequence if you have changes in internal standard area.
I believe we did do that on the biosolids, POTW. I didn't present that, and I don't know that we actually quantitated it. However, we added additional cleanups to mitigate any difficulty. It was truly amazing that if you clean up the sample appropriately, you don't get a lot of drift from that either. So. No, I didn't see a lot of drift, but I don't have that available at the moment.
Okay. Second question is, could you please explain the extraction recovery? Is it absolute recovery or corrected recovery via the D6 isotope?
The only thing we corrected for was what was found in the actual control itself. So if I can go back to no, it wasn't necessary. The D6 corrected for variation. There were the same concentration in both, so there was no correction for D6.
Okay. Another question is, what LOQ can be obtained by speeming?
That's a good question. The lowest standard we shot was in this 0.002 nanogram per mil, I believe. So that would be less the PPQ. I'm not sure, but it's very low. So as you can see here, you can see the low point. This was 1 nanogram per mil. We were in the 0.5 nanogram per liter area. So 0.5 PPT.
Okay. Says, how stable is the 0.1%, I can't read this word, I think it means soil solution or something solution.
0.1% peanut oil solution, maybe?
Peanut oil solution, yeah.
It's stable for a couple of weeks. So what you have to watch is that it's very absorptive, so it can be easily contaminated if you don't keep it very clean and separate from your analyses.
Okay. So you're getting some good questions in now. It says, can you say a bit more about how to measure both free and total concentration with SPME?
I could. I believe Dr. Gann's following presentation will be present, and but essentially what we do is we calculate the ratios for free, so they reside in an equilibrium. I think it would be best for Dr. Gann, maybe he can share in the next presentation.
Okay, so if the question is not fully resolved by the end, then we'll come back to it.
Okay.
After the other presentation.
I
also,
do have,
go ahead.
I'm sorry. I do have all of the calculations to back up how you handle that. That's available also. There was another full presentation that I have on SPME work alone, which I'd be happy to share with anybody, and in particular the person that asked the question.
Wonderful. Okay, so we'll make sure to connect you. Another question is, do varying levels of DOC and TOC impact the quantitation by SPME?
They do to a degree. The absorption, obviously, the varying levels, the higher the TOC or whatever, the less free is available. So yes, they do. But not in the vial. I mean, the vial is pretty typically clean. We centrifuge it at high speed. The sample itself is very clear, and we've had good success and reproducibility with what we've run.
Okay. And the last question is, what technique would you use to get GLP results at low concentration? SPME results are not accepted by regulatory agencies as quantitative.
We're currently working on that. The Pyrethroid working group has invested in a project that we're currently working on for submission in December. Once that occurs, we'll find out what EPA has to say about it. So it's a progression that will occur. Pyrethroid working group continues to work on it at this time.
Oh, and one last question came in. Is procedural calibration used?
Would that I guess I don't understand the question. I guess I can answer it in two ways. Sure. The external calibration is used with the use of D6IS. So what we do is we'll create an external calibration curve, and with the native to D6IS, and then the comparison of the sample, that ratio is pulled from the curve, yes.
Great. Okay. Well, thanks to the audience for such wonderful questions, and we'll be glad to connect you with Kevin. If you have follow-up questions, you're welcome to follow up with him to get information on standards and methods.